Oh, hi. We just took a look at PV equals nRT, and what I'd like to do is do something where it's not an equation of state, where we're describing a gas. I'd like to do something where we describe a gas and then change that gas. So I brought in the balloon. Let me blow this balloon up. It's just my expelled air, which is a lot of nitrogen because I breathe in nitrogen and breathe it out, a little bit of unused oxygen and quite a bit of carbon dioxide, my exhaust products, and water. I'll put this balloon inside of a little dish here. I was hoping that I didn't blow it up so large that it would fit, but I blew it up too large and the balloon doesn't fit in the dish. But I think I can remedy that because I happen to have brought in some liquid nitrogen. Liquid nitrogen, you've probably seen it like in special effects in the movies, is nitrogen gas. The nitrogen gas molecule that's moving around, and we cool it down to about negative 196 centigrade, so it becomes a liquid. Let me go ahead and pour some liquid nitrogen into the dish over the balloon. Liquid nitrogen is extremely cold. It's used in doctors' offices now and then. Oh, a nurse practitioner or doctor will go ahead and take a cotton swab, dip it into the liquid nitrogen, making the cotton swab really cold, and then press it against a patient's skin somewhere where they might have a blemish like a wart, and it'll make it blister and the wart falls off hopefully or something. Very, very cold. So the balloon fits. The reason the balloon fits is because it has changed volume. I changed the temperature of the balloon and the volume of the balloon changes. Now I assure you, the balloon did not pop. There are no molecules that have escaped the balloon going from the inside to the outside. And let me prove it to you. Let me take the balloon out and let it warm back up. Now, if gas had escaped from the balloon wouldn't be spontaneously regenerating its shape. You know, it would be like I'd need to pump it up, but it is. See, what's happened is the molecules on the inside of the balloon from the gas phase moving around real fast began to slow down. So they're banging on the inside of the wall of this balloon at a much slower velocity. They've slowed down, and the outside gas, they're still going at the same velocity. So the pressure on the outside, think of it for like a moment, has pushed in and collapsed the balloon. But every moment that this outside pressure is pushing in, you're okay, everything's all right. Every time the pressure is pushing in, that's okay because the balloon changes shape. The pressure on the outside 1 atmosphere is the same as the pressure inside 1 atmosphere. The balloon adjusts. Things that don't adjust shape are things like thermos bottles or sealed containers. The gas tank is not allowed to change shape. We open the valve, the pressure goes ahead and you could say changes for a moment. On the inside, the pressure is going down as gas leaves. But the change of the shape? No, it's a stainless steel container. It doesn't change volume. So, went ahead and changed the volume of this by changing the temperature. Let's set up a little relationship on this. And I do like putting that back in. Ooh, you know what I brought in? I'll tell you. Brought in a brand new racquetball. I'll put that rubber racquetball inside there and we'll cool that down while we do this. Many of you have seen a relationship like this before where you take PV equals nRT, PV equals nRT, and move everything to one side except for a constant. In our case, the constant is R. So if I divide both sides by NT, I'll have PV over NT is equal to R, which is a constant. So what I've done so far is not really a math derivation, but I'm showing a relationship. If we change something on the left side, the right side doesn't change. It's a constant, 0.0821 if that's what you're going to use, liter atmospheres over moles Kelvin. So if I change something over here and this can't change, something else on the left side needs to change. That's what happened with the balloon. I went ahead and changed T, the temperature, and the volume changed. With a balloon, the volume changes. If you were to have like a thermos cup full of soup and you put the lid on, you could actually go ahead and do some damage. You can put a flame or put it on a stove and you can get that thing to heat up so much, the volume wouldn't change, but the molecules inside, the gas molecules above the soup, would start going so fast you'd increase the pressure and then a bad thing would happen. It would explode and then the volume would change because it broke. Having put this together, I can put together a before and after case. P1 V1 over N1 T1. and the little ones are saying case number 1, like before the balloon goes in, I could call that case number 1, is equal to P2 V2 over N2 T2. Case number 2, after you cool down the balloon. Let me put a rectangle around this expression. It's this fabulous little expression that allows us to do what we call special cases. We have a balloon and we change its condition. We cool it. We have case number 2. We have a thermos bottle and we heat it up. Pressure on the inside changes. Again, when you heat or cool a balloon, the volume changes. The nature of the balloon is it's a flexible wall container. It can change volume, like demonstrated. A thermos bottle would not change volume. When you change the temperature, it changes pressure. Most of the time, we can cancel out the number of moles. And the reason we can do that is because nobody's opening up the balloon and allowing more gas to go in or gas to go out. We like it to have same amount before and after. We're usually changing the temperature. Now for the balloon has the same pressure before and after, so we can cancel these pressures for a balloon. If we were doing a thermos bottle problem, we would cancel the volumes and calculate the new pressures. So let's go ahead and do a little example here. Case number 1, a student obtains a balloon. Let's call it a 2-liter balloon, about the same size as one of these 2-liter soda bottles. The temperature, 300 kelvins. If you're provided a temperature or you measure temperature in centigrade, change it. We need to use the absolute temperature scale. If you're not convinced, do it in centigrade and see what happens. You'll have a mess. And then the student's going to take this balloon and they're going to cool it. So in case number 2, our balloon is no longer going to be 2 liters. When we cool it, it's going to shrink. Let's say that we cool it down to 100 Kelvin. Well, let's set this thing up. We have V1 over T1 is equal to V2 over T2, and we'll plug in our knowns. Volume at the beginning, 2.00 liters. The temperature at the beginning, 300 kelvins. Volume afterwards, I don't know, let's call it V2. That's what we're going to solve for. What's the new volume? And temperature, once we do the experiment, 100. The math is simple. We're going to do some cross multiplication. We're going to multiply 2 liters times 100 kelvins. Then we're going to have on the other side of the equality 300 kelvins times V2. Let me show this written out. We're going to cross multiply 2.00 liters times 100 kelvins. Cross multiply. That's equal to 300 kelvins times our unknown quantity, the volume afterwards. Well, units will work out fine because on the left side we have liters times kelvins. On the right we have kelvins, so when we divide both sides by 300 kelvins, the kelvins will cancel. So let's divide both sides by 300 kelvins. The reason for doing that is because we want to solve for V2. We want V2 all by itself. That's going to cancel this, and our math is 2 times 100 divided by 3. And I come up with a new volume of 2/3 of a liter, or I'll call it 0.667 liters. The balloon went from 2 liters down to 2/3 of a liter. Very good. Oh, a couple of moments ago I put the racquetball inside the liquid nitrogen. I thought I would come out here and listen to this. I'll drop it on the ground. Oh, that's a shame. It broke. The natural rubber product used to make the ball became very, very, very rigid, and so it shattered.